An inflection point, excuse me, is a point where the concavity of our graph changes. So our curve switches from being concave up to concave down, or vice versa. So for instance, if we had a curve that started like this, so this would start to be that bowl shape. Even though we're not extending it the other way, it still has half of that shape. So we've got a curve that starts off being concave up and then switches to being concave down. We could look at the sign chart for the second derivative of our function. And what we would see is values where the second derivative is positive, and then values where the second derivative is negative. So that would make this point x equals 0 an inflection point because concavity changes from positive to negative. Or similarly, we could have a curve that starts off being concave down and then changes to being concave up. So what we would see again are values where the second derivative is positive, values where the second derivative is negative. So since our concavity changed from negative to positive, again, we'd have an inflection point here. So what we're looking for is where is our graph the upside down bowl shape and where is it that right side up bowl shape. To find any inflection points, what we want to do is construct a sign chart for the second derivative of our function by first identifying all critical values for the second derivative. And critical values here are the same idea as what they were in module 7.1. We're looking for where is our second derivative equal to 0, or where is our second derivative undefined, or where does that not exist. So we again have a few different cases to consider when we find these critical values. The first would be that we have an inflection point. So this is going to be the same pretty much as the example that I sketched out above. We have a curve that starts off being concave up and then changes to being concave down. So looking at our second derivative, we would have a point where either the second derivative was equal to 0 or undefined. And in this case, we would see concavity change from positive to negative or from up to down. So that would make x equals 0 an inflection point. And the reason being, again, because the concavity changed. Case 2 would be that we find a point where the concavity changes, but we don't have an inflection point. So this would occur if we started off with a function that was concave up, we hit a point where the function was undefined, and then it changes to being concave down. So looking at our second derivative, we would again have a point where either the second derivative is equal to 0 or is undefined, and concavity is changing from positive to negative. So here, concavity changes, but the function is undefined at x equals 0. So while our concavity does change, this is not an inflection point because our function, the original function, would be undefined at 0, represented by that open circle. So we're interested in where concavity changes, but we can only classify it as an inflection point if the function is defined at that value. If concavity changes, it's not an inflection point if the original function is not defined for that value. And then the last case is where neither of those things occur. So we could find a point where the second derivative would have a value where it's equal to 0, but concavity doesn't change. So on either side of that critical value, the second derivative is positive, or in a similar but different situation, on either side of that critical value, concavity remains negative. So just because we have a critical value identified doesn't guarantee that concavity is going to change, and just because concavity changes doesn't guarantee that we're going to have an inflection point. So we have these three different cases to consider and keep in mind.